Hello. So, following our previous lecture about rigid body dynamics, now I'm going to solve an example which involves rigid bodies in its most simplified form. What we have here is we have two wheels, a large one and a small one, and the tape which essentially used to transfer motion from one wheel to the next. So we frequently see this in practice. So we have an element, a machine component, which is used to transfer power from one component, one rotating component, to the other one. We use tapes, we use chain and sprockets and things like that. In this case, so we have this tape and we have no slip condition. So we designed a paid tape such that the tape doesn't slip. And then we have a smaller one, which is 9 inches. This is the larger wheel, which is 15 inches. The tape goes like this. And then also that this plastic tape, once it's system set up, this tape is at this point when it starts to operate the system, it's going to be a rigid component, meaning that each 2 points on this tape do not move with respect to each other. So if you think about 1 point on this tape moves in this direction along its direction. The velocity is going to be along this direction, and same as acceleration, right? Because if you had an acceleration component in this direction, then this would essentially cause, after some time, it creates a velocity component, and then the tape goes also up and down as well as going straight, move linearly. So what happens is we're going to assume that our tape only has one velocity component, and it's pretty much true once the tape is stretched enough. Once the tape is in tension, it's pretty much true that we only have one velocity component along its length, and then we also have one acceleration component along its length. Now, let's say that the velocity of this tape goes from 2 feet per second to 4 feet per second, and it increases uniformly, so during 4 seconds time. So delta t, so initially the velocity was 2 feet per second, and now it's 4 feet per second. And then it's asking us to compute the angular acceleration of B and A and the number of revolutions of B during this delta t. So now if you think about it, this velocity increases uniformly. And as it increases uniformly, if you think about this tape, if I consider a point on this tape, any point on this tape, the velocity is obviously along its length. For this point on this tape, the velocity increases uniformly from 2 feet to 4 feet per second. This is true for this point. This is true for this point. And this is true for this point. Any point on this tape. So we know that velocity goes from 2 feet per second to 4 feet per second uniformly during this delta t. So we can go back to our fundamental relationship between velocity and acceleration and compute the translational acceleration of this tape for any point on this tape, right? So what we're going to say is this: we have this fundamental solution. We have this fundamental relationship between the velocity and acceleration. So solution. We have v at time t, or at time t is v0 plus a delta t. Right? This is the fundamental relationship. If we integrate the relationship between acceleration and velocity, we get this equation. So we know that after 4 seconds, let's say initially our time is equal to 0, delta t is equal to 4. So when t is equal to 0, v0 is 2 feet per second. So, and when time is equal to 4 seconds, the velocity is 4. So what I have here is 4 equals 2 plus a multiplied delta t, which was 4. So from this, a acceleration is half feet per second square. The translational velocity of each point on this tape is equal to half feet per second square. Now, the problem asks us to compute angular acceleration of B and A. Now, okay, think about it this way. So when we talked about acceleration in rotating frame and then rigid body rotation, acceleration in rigid body, we said that the acceleration for any point in a rigid body has 2 components. So for example, think about it this way. If it's easier for you, think about this being your rotating frame. Right? And think about this as being your inertial frame. Right? And then this frame rotates with an angular acceleration, angular velocity, and angular acceleration. Right? And this point on the wheel only rotates with respect to this point, right? So if you think about wheel as your rigid body, then that wheel, any point on the circumference of this wheel has two acceleration component. We said that a tangential acceleration component and a centripetal acceleration component. So what was our tangential acceleration component? So the tangential, if you go back to your notes or watch the other video, so tangential acceleration was omega dot cross r. And we said that we also show this as alpha cross r. Right? Now in this case, this is my r on the plane, right, in this direction, and my omega or alpha points out. Now, omega cross r, at least the magnitude of this component is going to be equal to, because the angle between the alpha and r is 90, sine 90 is equal to 1, and the magnitude of angular acceleration is equal to alpha r, right? So the magnitude and r is the radius of wheel B, or it could be the radius of wheel A, right? So again, translational acceleration is for any point on this tape. So you can consider a point on circumference of wheel A or circumference of wheel B. All right, so now that we have that, so for any point, we said that translational acceleration is equal to half feet per second. And at any point, we mentioned that the translational acceleration for the tape is tangent to the tape. So if you think about, for example, this point, this translational acceleration is tangent to this tape. Right? So simultaneously, it is tangent to the circumference of this wheel. So at this point, because we have no slip condition, the tangential acceleration of the wheel is equal to translational acceleration of the tape. Right? So I could say that because of no slip, A should be equal to alpha r. Otherwise, if it wasn't equal to alpha r, the tape would slip on this wheel. Excuse me. right? All right. So this is all we need, because we have A, we have R for both A and B. So all we need to do is, for example, for B, we have alpha B equals A over RB. This was 0.5 second square. And then we have RB, which is 1.25 feet. Remember to change the unit, and this is going to be 0.4 per second square. And for A, you can do the same thing, and for A, alpha A is 0.667 per second square. This is part 1 of this problem. In part B, it asks the number of revolution of B during delta t. So as this tape increases, the velocity of this tape is increased. For example, let's say this tape on the other side is connected to a motor. So the velocity, as we pull this tape, we increase the velocity of this tape. All right, so all we need to pay attention. Okay, this was part A. Part B. Okay, so what do we have here? What we have up to now is we have translational acceleration of the tape. We have also the angular velocities, right? And so we have both alpha B and alpha A. Right? So the question is then, how do we relate alpha B, the angular acceleration, to number of revolutions? So we know that alpha B is d omega b dt, or delta omega b delta t. And we know that omega is d theta over dt. That's called theta b. Right? So just like a translational acceleration and the relationship between translational acceleration and displacement, we can simply integrate this equation 2 times and compute that. It is pretty straightforward, so I'm not going to go through the details. Theta b is theta 0 plus omega 0 t plus half alpha b t squared. All right, so you can already see that, for example, this resembles to a projectile motion that you have seen in high school. All right, so we have theta b, theta 0. So what we are looking for is theta b, essentially. We're going to assume that we start the motion from 0 displacement or 0 angular displacement. In other words, theta 0 is equal to 0. And then this is going to be 0 plus omega 0, again, to remind you from rigid body, the motion of rigid body, we said that velocity is r omega. All right, so just like same relationship we have here, the magnitude of velocity is equal to r omega. So what I'm going to do is I'm going to replace omega with v over r. And if we were looking for number of revolution for VA, we would replace theta b with theta a, and then omega 0 would be v0 over RA. Right? And this is all we're looking for, because we know v0, which was 2 feet per second. So from this, we have theta b equal to 2 over 1 to 25 t squared, and then t is equal to 4 seconds. Sorry, I've used t instead of delta t. Remember, this is delta t, obviously. So theta b is going to be simply, so you replace t with 4, and to compute this number, theta b is going to be 9.6. Remember, this is radians. All right, so you would say 9.6 over 2 pi. It gives me 1.528 revolutions. All right, just to remind you again what we had, just review what we had. We had this tape going through these 2 wheels. The tape is already stretched. At this point, the distance between each 2 points on this tape does not change. The velocity of the tape goes from 2 feet per second to 4 feet per second. It goes up uniformly, so the acceleration is constant. So we compute the translational acceleration of the tape. We know that we have no slip condition, so at any point on this tape, when it's in contact with the wheel, you can assume that the velocity and acceleration of the tape and wheel are the same. We use that, the tangential acceleration and velocity of the wheel. So the tangential, we set the tangential component of acceleration of the wheel equal to our acceleration of tape at this point. And from that, we computed angular acceleration. Then 2 ways you can solve part 2. You can use the definition of angular acceleration. And the other thing you can do that I did not do here is you can use the fact that we have no slip condition at this point. The velocity of translational velocity of the wheel is equal of the tape, and the velocity of the wheel, which is r omega, are the same. So you can start with that, integrate that, and compute displacement. Yeah, that's it for today. See you next time.